Welcome back. At this point, we have seen the derivation of the mass on the spring equation, which gave rise to a second-order linear homogeneous differential equation, and we're using constant coefficients. Today, we are going to look at the case of the mass on the spring when there is no damping. This is going to give rise to two solution forms that we will discuss. Why do we get two solution forms? The roots of the characteristic equation that arise when we look at the mass spring ODE with no damping happen to be complex. It turns out that our exponential formulas for finding the solution work fine when the roots are complex. Why is that? Because we have Euler's formula to help us translate between the exponential of a complex number and the sine and cosine. What kind of motion would we expect to see in an undamped mass spring system? There is a demo online that you can go to here. Let's take a look. At this website, for which you have the link, let's go into the lab section. And in this section, you have several choices that allow you to take a look at a mass spring system. You can attach a mass to a spring. You can vary the mass. You can vary the spring constant. You can make it stiffer or less stiff. And you can vary how much damping there is in the system. Now, when there's a lot of damping, if you set the mass in motion, clearly the mass is going to come to rest fairly quickly. The system we are going to look at has no damping. So when you set the mass in motion, the mass is going to keep going indefinitely. How would you describe that kind of motion with a mathematical function? Coming back to our notes, let's think about it. I think many of you will have come up with the idea that such oscillating motion that never stops could easily be described by a sine or cosine function. Now, just a reminder, in our mass spring system, we called m the mass and k the spring constant. The term cy prime was our damping term. In this case, when there's no damping, of course, we set c to 0. Now, in order to help us understand the motion of this spring a little more, we are going to write our equation in normal form and define k to be omega squared m, which leads us to the normal form of the equation, where there is a 1 in front of the y double prime term. But it's not just the normal form that is useful. In this case, we can also think about how to isolate the omega term, or omega squared, which is k over m. It turns out that omega is the frequency of the oscillation. What units do you think omega should have? If you look at unit matching here, we note that y, the displacement, is distance. So the second derivative of y has units distance over time squared. Since we need all terms in the ODE that are being summed together to share the same units, and since y has units time, that means we need omega squared to have units 1 over time squared. And therefore, omega has units of 1 over time. All right, now let's talk about finding the solution to this differential equation. I suggest you pause the video and write down the characteristic equation, find the roots of the characteristic equation, write down what the basis of the solution space is, and then what the general solution is. Okay. The associated characteristic equation for this ODE is going to be lambda squared plus omega squared equals 0. To find the roots, we factor. Therefore, we have two roots. This puts us in the case where lambda 1 and lambda 2 are unequal. So we already know what the basis for the solution space will be in this case. It will be the two linearly independent functions, e to the I omega t and e to the minus I omega t. The general solution, therefore, has the following form. It is a linear combination of the two basis functions. All right, why do we have Euler's formula written here? This is going to allow us to take the form of the solution that we have just written as complex exponentials and convert into sine and cosine. I'm going to move below these boxes here, and we'll come back to the green and purple boxes in a second. Let's do the conversion now. Through Euler's formula, we know that e to the I omega t is cosine omega t plus I sine omega t. and that e to the minus I omega t is the same as saying e to the I minus omega t, which is then cosine of minus omega t plus I sine of minus omega t, which equals cosine omega t minus I sine omega t. Recall that because of the symmetry of cosine, we can just drop the minus sign inside, and because of the anti-symmetry of sine, we pull the minus sign out in front. So now we have a way to rewrite our general solution in terms of our new basis functions. Plugging in directly, we have that y of t equals a linear combination of cosine omega t plus I sine omega t and cosine omega t minus I sine omega t. Notice that this is our e to the I omega t, and this is our e to the minus I omega t. All right, this doesn't really help me yet, so I'm going to do a little bit of reorganization. I am collecting all the cosine terms and all the sine terms, which gives me a new coefficient in front of cosine, which I will call A, and a new coefficient in front of sine, which I will call B. So I am renaming the constants. Now I can write my general solution in the following form. Y of t now looks like a linear combination of cosine omega t with sine omega t. Now here's something interesting. The constants, the coefficients A and B, are actually real numbers. Why are they real numbers? It turns out that C1 and C2 always come in complex conjugate pairs. Since C1 and C2 are complex conjugates, this means that when you sum C1 and C2, that is going to be a real number. And similarly, if you take the difference between C1 and C2, but multiply by the square root of -1, represented by I, that will also be a real number. And you notice that our constant A is the sum of C1 and C2, and our constant B is the difference of C1 and C2 multiplied by the number I. I'll tell you in a moment why it is that we know that C1 and C2 can come in complex conjugate pairs. But for now, what I'm going to do is go back just to make sure that we have actually found the solution. So let's look at our green box. Is it the case that cosine omega t and sine omega t are in fact solutions to the ODE that we found? Because remember, we didn't solve for those directly. We found cosine and sine by taking our exponential solution and converting it to sine and cosine through Euler's formula. Well, let's see. If you take the second derivative of cosine, you can see it actually equals the first derivative of minus omega sine omega t, which gives you minus omega squared cosine omega t. And similarly, if you take the second derivative of sine, you see that that gives you minus omega squared sine omega t. And so both cosine and sine do satisfy our original ODE. Now, how did we know that was going to happen? Let's look at our purple box here. You can use the fact that the solution space of the differential equation is a vector space. That is exactly what we did. Any linear combination of two solutions, y1 and y2, must also be a solution. We talked about that last time. If you take y1 plus y2 over 2, that gives me cosine omega t. And if you take y1 minus y2 over 2i, that gives me sine omega t through Euler's formula. So that is another way to know that cosine and sine must be solutions to the differential equation because they are simply functions that you can create from taking a linear combination of your basis functions e to the I omega t and e to the minus I omega t. That tells us about how to move back and forth between the solutions of form e to the I omega t and e to the minus I omega t and solutions of the form cosine omega t and sine omega t. Now, as a bonus, I'm going to talk a little bit about how it is that we know that the coefficients C1 and C2 that come out of our solution process here, our coefficients C1 and C2, when we write our original general solution as C1 e to the omega t plus C2 e to the minus I omega t, what is it that guarantees that C1 and C2 will be complex conjugates of each other? We have to think about this in terms of not just the ordinary differential equation, but also the initial conditions. So starting with the fact that we have general solution C1 e to the I omega t plus C2 e to the minus I omega t, how are we going to find those coefficients C1 and C2? We find them by using the two initial conditions that will give us a unique solution. Those initial conditions usually come in the form of specifying what the function y is at initial time and what its first derivative is at initial time. And we are going to call those values y1 and y2. Because we are working in a physical space, we are going to say that y1 and y2 must be real. Now, in order to apply the initial conditions, we do have to calculate y prime. And remember, we compute y prime before we plug in time equals 0. This is a computation that I know you can all do because we are simply taking the derivative of the exponential, one of our favorite kinds of derivatives to take. Now, I suggest that you pause the video and take a second to actually plug in these initial conditions and see what you get when you solve for C1 and C2. See if you can convince yourself that C1 and C2 do have to be complex conjugates. All right, let's plug in time 0 to our values. Our solution y at time 0 is going to be C1 plus C2, and we've been given by our initial conditions that that has value y1. Our derivative at time 0 is going to be I omega C1 minus I omega C2, and our initial conditions tell us that that has value y sub 2. Again, because this is a physical model, both y1 and y2 are real. When we solve for C1 and C2, I hope that what you got was the following. However you write these, you can see that C1 and C2 are in fact complex conjugates because we have the real part, y1 over 2, plus or minus I2 omega times y2. So since C1 and C2 are complex conjugates, when you combine them the way we did, as we can see here, C1 plus C2 will have to be real, and I times C1 minus C2 will also have to be real. Okay, that's it. When we come together in class, we are going to look more deeply at solution spaces for these masses on springs. See you soon.